This is TechSNAP, episode 426, recorded on March 31st, 2020. Hello and welcome to TechSNAP, Jupiter Broadcasting Systems, Network, and Administration podcast. My name is Wes, and I'm once again joined by Jim.
What's up, everybody?
Let's start things off today with some good news. WireGuard has finally made it to 1.0, and it's landed in kernel 5.6. Now, we've obviously spent plenty of time talking about WireGuard already, so you might be thinking, why is this a big deal? Jim, I really liked how you touched on this in your recent Rs article about what it means to be in tree.
Yeah, Wes, I'm really excited about WireGuard being in tree now. What that means is that you're not going to be relying any longer on like a PPA if you're on Ubuntu or a third-party repository or even building from source on other systems. And that's going to mean increased stability and reliability. No more DKMS builds.
Finally!
For those of you who aren't familiar, DKMS is Dynamic Kernel Management System. And what it really means is that when you've got a module that's out of tree, it needs to be compiled against your particular kernel version's source code headers. And when you install a new kernel, you have to recompile the source code against the new kernel's headers. DKMS will do that automatically for you when you install a new kernel, but it's not 100% reliable. And as anybody who's using either ZFS or WireGuard for long enough can probably tell you, every once in a while when you get a new kernel, something coughs up a hairball, you don't notice, you reboot a day, a week, a month later, and suddenly you don't have your module and you're wondering why everything's broken. All that kind of thing is going to go away now that WireGuard's in tree. Now, for most folks, they'll still be using WireGuard as a loadable kernel module. In most cases, it won't be statically built into the kernel, although it could be. It's going to be handled like many hardware drivers already are, just loaded dynamically as needed at boot time.
Right, but your distribution has taken care of matching it to your kernel and getting it compiled for you.
Well, you know, it's even a little bit better than that. Your distribution doesn't really have a whole lot to do there. I mean, right now, if a distribution adds WireGuard, the distribution actually has to package it and, you know, deal with it and coddle it, and they could get a version ahead or a version behind or whatever. But with it being in tree for the actual kernel, it's just going to get built when the kernel does, whether the distro chooses to build it in statically or have it as a loadable module.
Right, you'll just see it when you're configuring the kernel.
And don't get us wrong, it's still going to be a little while before we're seeing the 5.6 kernel everywhere in the wild. There are some bleeding edge type distros like Gentoo or Arch or even Intel Clear Linux where you'll see the 5.6 kernel available pretty much immediately. But the slower moving, more stable distros like Ubuntu or CentOS, what have you, it's going to be a year or two before we see 5.6 kernels there. It's going to be even longer before we see 5.6 and up kernels in use in embedded devices everywhere. But at this point, the writing's on the wall. With WireGuard being in tree with 5.6, that means before you know it, everywhere you find Linux, you'll find WireGuard. And with it being universally available, once it is, it's hard to believe that more and more people won't be using it.
Yeah, you're definitely right about that prediction, Jim. Especially since there's backports available for Ubuntu 2004, Debian Buster, and via the compat layer to kernels 5.4 and 5.5. At this point, you're going to have to try if you want to avoid WireGuard. Well, this is definitely great news for us Linux users. I've also used it on macOS a little bit, where it's in the App Store and is pretty easy to get started with, even if it's running the user space daemon. One platform I haven't really tried is Windows, but Jim, I know you've got some clients using it.
Yeah, I do. At this point, I've got probably 20 or so end users using WireGuard on Windows. They have been for a couple of months, and it's been great. All of them have been extremely happy with it. They have noticed the difference moving from OpenVPN to WireGuard, and they have not had problems with it.
Really?
Yeah, WireGuard on Windows itself now, the Windows port has not reached 1.0. The Windows port is currently at 0.38, which lead developer Jason Donenveld describes as beta and says is nearing release quality. With that said, as you know, beta in the open source world means a very different thing from beta in the proprietary world. And I haven't had any complaints. The only real issue that you might have with WireGuard on Windows is it does require local administrator access. If you don't have administrator privileges on Windows, you won't be able to start or stop or modify the tunnels. So it's not really going to work for an environment where you've got your users locked down and restricted.
Of course, WireGuard inclusion wasn't the only goodie in kernel 5.6. There's also an interesting new file system, if you can call it that, called zonefs. But before we get into just what zonefs is and why it exists, I think we need to talk a little bit more about SMR. We've talked a little bit about SMR technology previously in the show, but mostly to warn about the performance implications of using an SMR disk. And that's because of some of the fundamental differences to how it works, especially compared to traditional PMR, or perpendicular magnetic recording disks.
If you look at a graphic map of how the bits are written to the disk, PMR and SMR look more alike than they do differently. You're still looking at bits that are longer than they are wide, and they're still laid out narrow side to narrow side from each other. The difference is that while the PMR bits are the entire width of the track and they're directly next to one another, the Shingled Magnetic Recording bits are only a portion of the width of the track, and they're kind of staggered in a diagonal pattern across the track as the disk moves forward.
Now, obviously, using this shingling technique means you can get greater storage density and store more bits in the same amount of space. But unfortunately, once the tracks are overlapped, you can't write to them independently anymore. In order to deal with that constraint, the disk surface is then divided into zones, with a gap left between zones. That means each zone can be written and erased independently.
What you can't do is overwrite part of a zone. Once you begin writing to a zone, you've begun writing to it, and you have to continue writing sequentially in order. You can't do random access, and you can't overwrite an individual bit. Once you want to change something, you've got to start back at the beginning and write all the way through the zone to the end again.
Yeah, those are some unusual constraints, and that means there's a couple different approaches to dealing with them. The traditional approach just sort of assumes the device firmware is handling that internally, and then you just expose a normal interface to the host, and that's what you might see on some SMR drives or on SSDs.
And while both SMR disks and solid-state drives are typically going to be zoned block devices with all the limitations that we've talked about, and they're managed by firmware internally and exposed as a normal raw block device to the operating system, there are real performance constraints involved in breaking this zoned schema. Now, on solid-state drives, we didn't really worry about that because the performance was already so incredibly higher than what we were used to from conventional disks that we just accepted it as a cost of doing business. And for the most part, today, most people are still just going to accept it. Very few people who are getting 90,000 IOPS and 300 or 400 megabytes per second of throughput on their solid-state disk are going to be like, you know what? This thing's too slow. We need to figure out why. Shingled Magnetic Recording hard drives, though, that's a different story. Now you're starting with a conventional disk that already really didn't have great performance, seems to have really terrible performance now that we're used to solid-state disks, and you lump Shingled Magnetic Recording on top of that in the zoned access, and now you're looking at sequential write performance that can be 40 megabytes per second or lower, and random access performance that, well, I don't even want to talk about.
Now, I'll admit, we did have to do a little research for this story. I couldn't have told you what zone storage was, and honestly, after reading the first couple paragraphs, I still couldn't.
Yeah, I didn't know either, Wes. Of course, as it turns out, zone storage really effectively means SMR disks and solid-state drives, but I'd never heard the term, so I went Googling for it after learning about zonefs and that zone storage was a thing. And I got to tell you, Western Digital's definition of it was not very helpful. I'm going to go ahead and quote from the leading paragraph on their blog, and I'm going to do it with a voice that I think is appropriate. Are you ready?
All right, let's hear it.
Zoned storage is a new paradigm in storage, motivated by the incredible explosion of data. Our data-driven society is increasingly dependent on data for everyday life, and extreme-scale data management is becoming a necessity. Already today, large-scale data infrastructures utilize tens of thousands of hard drives and solid-state drives. Hyperscale companies need to be able to carefully manage them from a global perspective in a cost-effective way. Zoned block device technologies were introduced with the goal of moving us towards efficient data management and large-scale infrastructure deployments. I don't know any more now than I did before reading that paragraph.
100% marketing, 0% content. Honestly, at this point, I'm just glad they didn't say synergy. Now, the Linux kernel has had support for zone storage starting way back in 2014 with some serious support beginning with kernel 4.10 in early 2017. But a lot of these methods were lower level. They were introduced as an interface to the block layer or as a new component for device mapper. What's new in kernel 5.6, though, is a simple interface to zones known as zonefs. The goal of zonefs? It is really simple. It just exposes each zone of a zoned block device as a file. The intention with zonefs is to simplify implementation of applications that know they're going to be sitting on top of zone devices and want to optimize that. Some examples are databases that are using log-structured merge trees in the background, like BroxDB or LevelDB, and know they're going to run on top of zone block devices, because you can actually implement some algorithms to better take advantage of this right into the application. In effect, you're saying, no, I don't want the hardware to manage this. I don't trust that firmware. I'll do a better job right in my app. But instead of having to use something lower level like an ioctl or other kernel interface, you can just read and write right to the files yourself.
The other thing that I think we ought to make clear, Wes, is that zonefs is not really a file system at all in the normal sense. What it's doing is, like you said, it's exposing each individual zone as a file. But what makes this not a file system in the normal sense is you can't create a file, you delete a file, you can't rename a file. Really, zonefs it's almost more like the device system to begin with. You have these files, none of which you can rename or change or expand or anything else, but you know that you can write to that individual file and understand that it actually is a zone on an underlying zoned block device.
Right. Instead of obscure kernel APIs, you're back to the standard Unix read and write.
And the reason it makes sense to implement this as a sort of a pseudo file system, if you will, instead of just making all the individual zones available as individual block devices, is just the sheer number of them, particularly when you're talking about shingled magnetic disks. We've seen some papers talking about how these things might be laid out that used as an example a 10 terabyte shingled magnetic recording disk that had 256 megabyte zones. So we're talking tens of thousands of individual devices if you're exposing them as traditional block devices just right under dev. And I don't even want to issue an ls command on that personally.
Yikes. zonefs is certainly a neat feature to see, but I think it's really going to be useful for people running niche workloads at scale on this kind of hardware. But while researching it, we did notice another component in the Linux support for zoned storage that really stood out as something that might actually be useful in dealing with SMR disks.
Yeah, I got to be honest, Wes. When we first started looking into zonefs, my first thought was, well, that's not going to cause any confusion with ZFS. And my second thought on looking more at the technical details was, that's not a file system, and that's way too complicated for anything that I want to mess with. I want to be able to just install a file system. It doesn't have to be ZFS, but some file system. Maybe it's ext4, maybe it's XFS. And, I want to read and write my files. That's the majority of what I'm doing. That got me looking a little bit further, and I've came across dm-zond. Now, dm-zond is a portion of the device mapper stack introduced also by Western Digital with the 4.10 kernel. dm-zond looks a lot more potentially interesting. What it does is it exposes the underlying SMR disk or solid-state disk, which in turn exposes its individual zones to the kernel, and it aggregates the whole thing and then presents that as a device mapper block device that you can access as you normally would with a traditional file system and traditional input and output. I got to tell you, Wes, I'm itching to actually test that because I'm familiar with how bad the performance on SMR drives is when they're just exposed directly as a normal disk. I got to think that there's not much point in dm-zond if it doesn't alleviate a lot of that. And I'd love to find out more.
Right. This is another situation where instead of letting the firmware take care of it, dm-zond is doing that. It sets up its own caches and caches things until it can do a sequential write across a zone.
Now, you do sacrifice a little bit of your storage and a little bit of CPU and memory to running dm-zond, but it truly should be insignificant for just about anybody. And the example that we mentioned earlier with a 10 terabyte Shingled Magnetic Recording disk divided into 256 megabyte zones, we were only looking at a memory usage for the entire disk of 4.5 megabytes as most, and as little as 5 zones on disk used internally for storing metadata and performing reclaim operations. Now, 5 256 megabyte zones, you're talking about a couple of gigs on a 10 terabyte disk. I think we'll be okay with that.
Yeah, DM Zone D looks pretty useful and interesting. Unfortunately, or maybe fortunately, I don't think I have any SMR drives right now. I say think because it turns out that's getting more confusing than it should be.
A user on the ZFS Discuss mailing list gave everybody a warning, actually just a day ago. Western Digital and Seagate both are, Stote's term was submarining drive-managed SMR drives into channels disguised as normal drives. He went on to explain that with the very popular Western Digital red line, you have to look at the suffix on the end of the drive number. The WD-Red NAS drives that we all know and love have EFRX as the suffix on the model number. But what we're starting to see now is EFAX drives showing up in the channel. And those are actually Shingled Magnetic Recording. Stote says if you try to resilver one of those things in a RAID Z3, you can expect mountains of errors before ZFS throws the drive out of the VDEV. When he checked it with Smart Control X, he found IDNF errors, sector ID not found, and he thinks that means because ZFS is asking the drive to look at a logical block that the drive hasn't actually recorded yet. And the nature of SMR means that unrecorded LBAs are completely unformatted. You can think of it as kind of like trying to read an uninitialized variable in a program. Smart long tests and everything else all come out 100% okay. The only clue that you really get about them being SMR, if you don't already know about the suffix, is sequential write speeds of about 40 megabytes per second, and the fact that they report a trim function. He goes on to complain a little bit more and says that the maximum amount of time he's managed to hold one of those drives in his array while it's being resilvered is about 2 hours before ZFS kicks it out. And at 40 megs a second, you'd need about 48 hours to write across one of these things if it was written sequentially. And resilvers aren't even written sequentially.
Yikes. That is definitely something to watch out for the next time you're buying some discs.
Wes, while I was looking into this, I came up with some unintended comedy that I feel like I've just got to share with you. On my own RZFS on Reddit, a user responding to this whole comment thread said, and I quote, "I have perhaps the most unpopular ZFS setup right now. It's literally a collection of USB SMR drives connected to low-power computers, exported via iSCSI, then RAID Z1 of those iSCSI targets on the ZFS file server. Are you angry yet?"
Yeah, I think I am.
Given all that, we are looking here at a write throughput, completely sequential, using DD, of around 26 megabytes per second, and a read throughput coming back off of the pool of about 56 megabytes per second. Now, obviously, that's nowhere near as fast as you would normally expect for a pool of 6 Rust disks. And pretty much any configuration with DD getting completely sequential workload. With that said, given the fact that we're looking at such inexpensive devices, unshucked USB drives connected over USB 2, to Raspberry Pis or similar, it's usable if that fits your workload. And I have to stress here, you're really careful to manage your redundancy and parity and make sure that you don't lose more devices than you can cope with. I could see that suiting somebody's needs.
Yeah, like you say, Jim, if it meets your needs, it's kind of a clever solution. Now, while we're speaking about disks and file systems, one that didn't quite make it into 5.6 but will be in 5.7 is exFAT. And unfortunately, that inclusion seems to be causing some hurt feelings.
Yeah, Wes, Paragon Software did not seem too happy about exFAT showing up the 5.7 kernel. Now, backtrack a little bit. exFAT is coming to the Linux kernel because Microsoft gave its blessings to it. Now, when Microsoft first designed exFAT as the go-to bare-bones file system for embedded devices like, cameras and anything else that uses an SD card, they had it pretty hedged up with defensive patents, and they were absolutely willing to go after anybody who infringed. In fact, for a long time, Microsoft was making more in licensing off of every Android phone sold than Google was, due to exFAT inclusion.
Well, look at how times have changed. Microsoft actually gave their blessing to the inclusion in the kernel by putting out the specification for the file system. There'd already been some proposed support using older Samsung code that really wasn't up to date, but after Microsoft announced that they're totally cool with it, the code that's landing in 5.7 is Samsung authored, up to date, and maintained by Samsung.
It's also actually entry in the production VFS stack where the earlier code was only available in staging.
This will be nice to see, as anyone who's tried to use an unfortunately formatted SD card is sure to understand.
Now, this made Paragon nervous because one of their revenue streams is in selling a proprietary implementation of exFAT for Linux and Mac and possibly other platforms as well. And it's hard to imagine that people are still really going to be lining up the door to hand Paragon license fees when there's a Microsoft-blessed and Samsung-developed exFAT implementation right there in the Linux kernel.
Yeah, no kidding. I can understand why they'd be a little upset about that. But boy, did they have some bad things to say about open source.
Yeah, it was really strange, Wes. I opened my email one day and there was this email from a Paragon executive. It was in two parts, and part two was fine. They mentioned that they had closed a deal with European cable modem vendor, basically Sagemcom, to provide their exFAT implementation on that company's cable modems and routers, presumably to act as kind of built-in all-in-one file servers with home gateway devices. That much was fine, but they led with several pages of open source FUD that wouldn't have looked out of place on Steve Ballmer's stationery in 1997.
That is a low bar. All right, well, they had, 3 cases where open source, quote unquote, didn't work?
Yeah, Wes, their choice of 3 cases supposedly parallel to the new exFAT in the Linux kernel, it was really odd. It felt like they were just digging, trying to find something they could pull out of a hat. They mentioned exFAT implementation in Android itself, and then NTFS implementation on Mac OS, and finally SMB, the network server message block protocol, its implementation on Mac OS. This was a really odd flex because the Android case was the only one that really had anything to do with exFAT. But if you know anything about the history of FAT on Android, it's a never-ending stream of open source solutions that get better over time. You read through it and you keep waiting for, the part where proprietary software comes in to save the day and make Paragon Software's point, and it just never gets there. Then moving on to Mac OS, they try to make a big deal out of the inferior NTFS support built into Mac OS. The problem there is that Apple never cared about NTFS support. The only reason it ever showed up at all is because in Panther 10.3, they literally just inherited the VFS stack that already existed in FreeBSD that had an older NTFS implementation. If they could not have gotten that for free, they would not have put it there. And for that matter, if you want full NTFS support on the Mac, you can still get it, and you can get it modern with NTFS 3G, just as you would use on the Linux side. It just has to get installed as a port. Now, their final weird flex was talking about SMB, the Windows file sharing network protocol, again, as it's implemented on the Macintosh. And they go on to say that Mac OS, as well as the majority of printer manufacturers, strange flex, don't rely on an open source solution, as there are several commercial implementations of SMB as soon as a commercial level of support is required. Now, this is weird on a number of levels. For one thing, if you want commercial support of Samba, the OG of Windows networking on other operating systems, you can absolutely get it. You can pay the Samba organization directly for support. In fact, they have a list of high-profile commercial vendors that they do support, including American Megatrends, Hewlett-Packard, Veritas, and VMware. We should also note the fact that Samba is used on pretty much everybody's network-attached storage server, which is where that protocol is the absolute most important. If you buy Synology NAS, it's using Samba. Netgear, Samba. QNAP, Samba.
Yeah, they really seem to be missing the point. And also, a lot of the tech they're talking about here, right? If we're thinking about FAT, if we're thinking about SMB, these are all cases where it would have been better from the start if we had an open source solution that all vendors could contribute to and make better. So now that we've got Microsoft blessed, Samsung authored and supported code, it sounds like it's going to work pretty darn well.
It does. You know, Wes, I also just couldn't help but laugh at the fact that they decided it was a good idea to mail me, of all people, a giant torrent of anti-Linux FUD. Granted, most PR people don't really look up a whole lot about the reporters that they're reaching out to. But man, sometimes you just got to do a better job of reading the room.
They didn't know who they were messing with. Let's move on from that negativity, move to something a little more exciting. We've got one more storage story for you today, and that's the intriguing work Cloudflare's been doing to speed up Linux disk encryption.
They've got a great, very detailed blog post outlining their whole journey through speeding up encryption on blog.cloudflare.com. But we can condense it down to the best bits for you. At the lowest level, it's important to know that they're using dm-crypt to do full disk encryption at the block level. But they weren't getting the performance that they expected to. No matter how fast the underlying disk was, even if it was a RAM disk, they couldn't get throughput better than about 166 megabytes per second. Now, these are on servers that have hardware acceleration for the crypto stuff, so they should have been getting far better performance than that. And they couldn't figure it out, so they posted for help to the dm-crypt mailing list.
Uh-oh.
If you've ever interacted with a developer mailing list on the internet, the response they got probably won't come as a huge surprise. Remember, this response is literally going to Cloudflare.
If the numbers disturb you, then this is from lack of understanding on your side. You are probably unaware that encryption is a heavyweight operation.
Seeing the humor in this response, the Cloudflare engineers decided to do a little bit of scientific research and type, "Is encryption expensive?" into Google search.
Hey, that's how I do it.
Yeah. One of the top results, which actually contains meaningful measurements, is their own post, but in the context of TLS. The gist is that modern crypto on modern hardware is very cheap, even at Cloudflare scale, doing millions of encrypted HTTP requests per second. In fact, it's so cheap that Cloudflare was the first provider to offer free SSL for everybody.
All right, so the encryption itself, that's not the problem. Cloudflare had to keep digging, so they started looking at dm-crypt itself. And originally, they sort of expected dm-crypt to be a simple proxy, which just encrypts and decrypts data as it flows through the stack. So you write some data into your device mapper device, it's going to encrypt it, and then pass it off down to whatever device you're really storing it on. And honestly, I kind of thought that's how it worked too. But it turns out it's a lot more complicated.
And we probably don't want to go too deep into the details, which are pretty extensive, of the cruft found in dm-crypt. But it does a lot of scheduling and queuing, and it'll hold on to a request and try to issue it at, quote, the right time, unquote, as though it were working directly with, you know, maybe a hard disk underneath, kind of like the way that completely fair queuing used to work when everybody complained about how much latency there was on their desktop. But the TLDR here is that Cloudflare was like, I don't think we need all this stuff. So they tried just cutting it out and turning dm-crypt back into what they originally thought it was, a simple, cheap wrapper that just encrypted data before passing it down to the disk. And it turns out, yep, that was the problem, and yes, cutting all that out fixed things. They have a really neat graph of the response times, both of a bare disk and the original dm-crypt and their dm-crypt that bypassed all the weird queuing stuff. The short version is, it looks like a city skyline, all the latency with the vanilla dm-crypt as it is in the kernel. Their version with all the queuing stuff bypassed is almost indistinguishable from the disk underneath it.
Say that again. It's almost undistinguishable with no encryption. I mean, at that kind of performance level, there's no excuse not to be encrypting at rest. Now, we should note that right now, if you'd like to give this a try yourself, you're going to have to go compile those modifications yourself, add the kernel modules, and then get to benchmarking. And Cloudflare acknowledges that right now, this is very much targeted and tuned to their infrastructure. Other setups on the huge array of hardware that Linux runs on, well, they might need some of this functionality that Cloudflare's removed. But it does sound like they've got upstream aspirations.
So Cloudflare will be submitting their work for inclusion into the Linux kernel, but they're going to change it up a little bit from their testing. Rather than just completely slicing out all the code that they don't want, they're going to go ahead and just turn on another dm-crypt setup flag that will allow you to use it Cloudflare style without all the extra stuff. But in case there's some workload out there that actually needs all that queuing, you'll be able to use it just as you always did the strange and slow way. It's not in the kernel yet, but it should be soon.
Yeah, I think this is a great lesson in revisiting your assumptions, taking a look at how things work now, and if it still makes sense in the light of new hardware and new APIs in the kernel, because sometimes you can actually double your performance by doing less. And I'll definitely be looking forward to seeing these changes in a future kernel, but for now, we better get out of here. I'd like to keep playing with kernel 5.6. If you're interested in any of the fascinating stuff we've talked about today, well, you'll find all the links over at techsnap.system/426. And over at techsnap.systems, you'll find our whole back catalog and easy ways to get in touch and subscribe to our feed. If that's not enough for you, head on over to jupiterbroadcasting.com, where you'll find the rest of Jupiter Broadcasting's fine productions. If you'd like more Jim, well, he's writing over at Ars Technica. And he's on Twitter at
JRSSNet.
I'm there too, at Wes Payne. And you can find the whole network at Jupiter Signal.
See you in a couple weeks, everybody.